the objectives and goals for today is just to be able to describe situations in terms of a specific frame of reference, which we'll revisit what a frame of reference is, obviously, and then to be able to solve problems that involve relative velocities. Okay? So, we've been talking a lot about motion, but it's important to remember that when you're discussing motion, frame of reference is really important, because if two people are observing motion and they're using different frames of reference, they're going to describe that motion much differently. So your frame of reference is whatever it is that you are using to compare your motion to. So if I'm riding on a bus, I can compare my motion to my seat, I can compare my motion to the bus, or I can compare my motion to the lamppost on the side of the road. And those would give me different motions, correct? Right? If I'm comparing myself to the bus, my velocity is 0. If I'm comparing myself to the lamppost, then my velocity is whatever the velocity of the bus is moving at is. Moving car's motion can be compared to the road, or you can compare a moving car's motion to another vehicle. And if that vehicle is in motion in a different direction, that's going to affect the motion as you describe it. Example, if I'm moving 80 kilometers per hour north and a car passes me going 90 kilometers per hour north, to me, it doesn't look like they're going 90 kilometers an hour, right? That's why when you're in a car and cars pass you, they don't appear to be going as fast as when you're standing on the side of the road and a car passes you, because you're comparing their velocity to different things. The car, as compared to the ground, is going 90 kilometers per hour north. The car, compared to you, is only going 10 kilometers per hour north, because your vehicle is already moving at 80 kilometers per hour to the north. So, we can indicate the frame of reference using subscripts. So you're going to see this a lot where they're going to just give you subscripts, and they will usually define the subscripts and tell you what these random letters mean. Okay? So we might say velocity subscript SE to mean the velocity of the slower car with respect to the earth. So the first letter is always going to tell you what you're measuring, and the second letter will tell you what you're comparing it to, what your frame of reference is. So V sub SE means velocity of the slow car as compared to the earth. In a similar way, we might say velocity FE, meaning the velocity of the fast car compared to the earth. So in the example that we did before, V sub SE would be 80 kilometers per hour north, and V sub FE would be 90 kilometers per hour to the north. Now, in the example problem that I gave you, it's pretty easy to figure out what the relative velocity between the two cars is, right? It seems like a pretty straightforward deal. It's not always going to be that easy, so we want a standardized way to solve for that relative velocity there, okay? And we're going to do that sometimes, not all the time, by using the subscripts to help us figure it out. So let's say we want the velocity of the fast car relative to the slow car now. So what we want is V sub Fs, right? In order to do that, we can use this equation. So velocity velocity of the fast car compared to the slow car is equal to velocity of the fast car compared to Earth plus velocity of the Earth as it compares to the slow car.
So that's different than slow car to the Earth.
Yes, it is. But very similar, and we're going to explain how.
Okay.
So, I want you to notice in that equation how we start with Fs and we have on the other side of the subscript, or of the equation, it starts with F and ends with S on both sides. So I'm going to go back and draw it. Actually, I'll just draw it on this page and show you what I mean. Okay, so we had VFS equals VFE plus VES. So notice how we start with F and end with S, and over here we start with F and end with S, and then this matches up. That's how we want to do these subscripts so that we come out with the correct answer. So there's a reason we used ES and not SE, and it's because we wanted it to go FEES so that those center E's are the same. So this is just the convention that we have set up. So if we want FS and we have FE and we need ES to get to FS. I know it seems a little strange. Okay. So in this, the velocity of Earth respective to the slower car is just equal to the negative of the velocity we have of the slower car compared to the Earth. Because if you think about it, they're just the same velocity but in opposite directions, right? If you're comparing the Earth to the car or the car to the Earth, the speed should be the same. It'll just be the direction that they're moving that's different, right? So we can wind up with this, where we have the velocity of the fast car relative to the slow car is equal to 90 kilometers per hour north plus our negative 80, or in this case I've just simplified it to be minus, because plus a negative is like a minus. Minus 80 kilometers per hour north is equal to 10 kilometers per hour north, which we talked about as being that relative velocity between the two earlier. This is just a method to find it. In general, the equation looks like this. If you're trying to solve for a velocity of AC, you can take AB plus BC to get AC. Notice once again how we start with A and end with C, and over here we start with A and end with C, and the intermediate ones are the same. So if you're looking to set something up, that's how you're going to need to set it up. Okay, here is another type of problem that you may see. Okay, the world's fastest current, so like an ocean current, is in Slingsby Channel, Canada, where the speed of the water sometimes reaches 30 kilometers per hour. Pretty fast. Suppose a motorboat is trying to cross that channel perpendicular to the bank at a speed of 18.0 kilometers per hour relative to the bank. Find the velocity of the motorboat relative to the water. Okay, so if you look here, I've drawn a picture for you, okay, where you can see we want to know, or we know what they're saying is the speed of the current, the water with respect to the bank, so that's V sub WB, and we know the velocity perpendicular to the channel, okay, because they said the motorboat crosses the bank at a speed of 18.0 kilometers per hour relative to the bank, so they're saying perpendicular to the channel, here is how fast it is moving, but we want to know the speed of the motorboat compared to the water, okay? So the reason we've drawn it as a triangle like this is that in order to cross the bank like this, you're going to have to put the boat at a significant angle because of how fast the water is moving. And the nice thing about this is that it allows us to solve for this resultant velocity over here using the tools of trigonometry that we have already established. So we can solve for this by saying the velocity of the motorboat compared to the water squared is equal to the velocity of the motorboat with respect to the bank squared plus the velocity of the water compared to the bank squared. And we can solve for the angle that the boat would be traveling at by doing theta equal to the inverse tan of the velocity of the water compared to the bank over the velocity of the motorboat compared to the bank. So just using some of the tools we have already figured out. So in this situation, the biggest hurdle to you solving the problem is being able to draw the picture, right? So being able to interpret from the question what this picture should look like in your brain. Okay? Because I have no doubt in my mind that you guys can do a squared plus b squared equals c squared and the tangent function. And that's what I think you'll find when you are thinking about relative velocity questions, is that it's the majority of the work is conceptual work in your brain, getting your brain thinking about the situation correctly, and the math on these should not be as challenging as the math on the other questions we've been doing. If you work this out, you should find that the velocity of the motorboat compared to the water should equal about 35.0 kilometers per hour, and that your theta should be roughly 59.0 degrees away from the oncoming current. Yes. Should be this angle right here. So oncoming current coming this way, and we are measuring like our away from the oncoming current. Okay, that's where we're going to end notes today.